What I want to do is spend a little time looking at determining boundaries of integration, the limits of integration for these double integrals, because a lot of times that's where we run into problems. So I've got some examples here. I've got a couple examples where I'm going to use rectangular coordinates and then a couple where I use polar. But let's look at this first one. Let's suppose we've got this function, z equals f of xy, and we've got this surface, and let's suppose it's above the xy plane. Below, down here on the xy plane, we've got this rectangle bordered by x equals 0, x equals 3, y equals 0, and y equals 2. In other words, this thing that I've drawn here. Now notice, we're working with rectangular coordinates, and we've got a rectangle. That seems like a perfect fit. So we're very encouraged by that. So we've got this double integral. Okay, let's just make this. We've got the height, which is f of xy. That's the height of this. We've got this solid, and for every xy point we have down here on the region, we're going to go up z, f of xy. Now, I'm going to integrate with respect to x first, and then with respect to y. And let's just see what happens. Let's see what x does as we vary y. Okay, so let's suppose we've got a y right here. Well, what does x do? Well, it starts at 0, and it shoots right over here to 3. If we choose a different y, what does x do? Well, it starts at 0, and it shoots right over here to 3. So no matter what y does, x goes from 0 to 3. And then the question is, well, what does y do? Well, y goes from 0 to 2. Yeah. So there we have it. Now, let's suppose we wanted to go the other way. Let's suppose that I wanted to integrate with respect to y first. So I've got this f of xy, and I want to integrate with respect to y first. Oops. Okay. Well, let's see what that's going to look like. So now we're saying, okay, for every x, I'm looking at the outside. For every x, what does y do? Well, y starts at 0, and it goes up to 2. I pick a x over here, 0 to 2. So y goes from 0 to 2 as x goes from 0 to 3. So these are two integrals that are two sets of integrals that we could use to calculate the volume that we're seeking. Now, notice how simple this is. We just had numbers. No algebraic expressions in here for our bounds of integration, just numbers. And that's because we just are integrating over a rectangular region. Now, let's suppose that the region is not rectangular, and we're still using rectangular coordinates. So let's suppose that now we're integrating over a trapezoid. Okay, so same thing, we're underneath the z equals f of xy, but now we've got our bounds of integration to be defined by this trapezoid. So let's see what happens. Let's set up our double integral here. Now, notice I've got a couple of options here. Let's just suppose I pick a y value right here. I pick this y value. What does x do? Well, it goes from right here all the way over to here. In other words, what x does is it goes from x to negative x plus 6. Or actually, look, if I choose a y, we're saying, well, what does x do? Let me go back. So let me put this in here, f of xy. And I'm going to integrate with respect to x first, and then y. So now I'm choosing y. So here's a y, and I go from here over to here. Okay. In other words, I go from that one slanted line to the other slanted line. That's what x does. Now, that means that x starts right here at, x equals y equals x. Put it in terms of y. Since I'm integrating with respect to x, I want this to be in terms of y. So I'm going to go from y up to here, up to over to this other one, and this is x equals 6 minus y. So 6 minus y. So notice, I'm integrating with respect to x. I want these boundaries to be in terms of y. So no matter what y I choose, x goes from y to 6 minus y. Yeah. Now what does y do? Well, y goes from 0 to 2. Like that. So you notice, since we don't have a perfectly rectangular region down there, it's a little bit, a trapezoid in this case, we do have variables in our bounds of integration. And since I'm integrating with respect to x, I need those bounds to be in terms of y. So, now, we don't have to integrate with respect to x first. However, it's the easier thing to do. So let's suppose that I want to integrate with respect to y first. Let's see what that looks like. Well, if we integrate with respect to y first, let's think about, what does x do? If I have an x right here, what does y do? Well, y goes from 0 up to x. If I pick an x here, what does y do? Well, y goes from 0 to x. Now, that happens until I get right here. And now notice that if I pick this x, y goes from 0 to 2. If I pick this x, y goes from 0 to 2. So this represents a different integral. So I've got one integral right there, another integral here, and then notice over here, if I pick this x, y goes from 0 to negative x plus 6. So this is going to require 3 double integrals if I integrate with respect to y first. So that's something to keep in mind. You want to make it easy on yourself. You would get the same result, but instead of 3 double integrals, it's better if we can just work with one. Now, let's go down here and look and see where polar would come in. Now notice, up here we had 2 examples. We had where we have just a rectangular region over which we're integrating. And then down here, we're still working with rectangular coordinates. However, it's a trapezoid. So instead of just having numbers up here when we're going over a rectangular region, okay, over this one, down here we have algebraic expressions. Now let's switch over to polar. Let's see what would happen here. If we were, this is an example where we're going to want to use polar, but let's just set it up with rectangular first. Okay, let's suppose I want to, I've got my height here, f of xy, and I'm going to integrate, it doesn't matter with respect to x or y, but notice on this one, let me just solve for y, and I get the square root, well, plus or minus the square root of 4 minus x squared. Okay, if I just solve that for y, this is what I get. So if I integrate with respect to y first, notice what happens. I'm going from negative, the square root of 4 minus x squared, to the positive 4 minus x squared. Okay, and let's just see what this looks like. So then integrate with respect to x. Now notice what we're saying. No matter how I choose x, y goes from down here all the way up to here. In other words, it goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. If I choose x over here, I go from down here to up here. So x goes from negative 2 to 2. See? Because the circle has a radius of 2. So it goes from negative 2 to 2. Okay, now, let's convert this to polar and see what this would look like. Now, if we convert it to polar, notice this x squared plus y squared equals 4. That's just r equals 2. Okay, so now we're going to look at it with polar. Now remember, when you convert to polar, this is going to be, you've got r cosine theta, r sine theta, and then you've got r dr d theta. So in other words, I've converted this thing to polar, but whenever I commit to the polar integration, I'm going to have to do r dr. That's got to be a part of it. Now now we're looking in terms of the radius. Well, what does the radius do? Well, it goes from 0 to the circle, right? It just goes from 0 to 2. So r goes from 0 to 2. And then if you think about, well, what does theta do? Well, theta goes all the way around this circle. In other words, theta goes from 0 to 2 pi. Now, dig this. We're in polar, and we've got a circle centered at the origin, and look what happens. We are only integrating over numbers. There's no thetas or anything in there. That's when we have a circle centered at the origin. So this is how we would set it up. Now, let's change that a little bit and say, okay, we're below this function and above this circle. Okay. Now let's see about how we would integrate this. Now, I'm going to first of all set this up with rectangular. Okay. So here I go, rectangular coordinates. So let me solve for y. So y is equal to plus or minus the square root of 4x minus x squared. Okay? And I've got f of xy. And now I want to integrate with respect to y first and then with respect to x. So what does y do? Well, y goes from negative 4x minus x squared to positive square root of 4 minus x squared. 4x minus x squared. There it goes. Let me write that a little better. Okay? So, no matter what x we choose, if I choose an x here, I'm going to go from here, down here, all the way up to here. Okay? No matter what x I choose, from here up to here. Now, this is a circle, so this tells us maybe we're going to want to use polar. Now, let's just take a minute and dig what we have here. We have x squared minus 4x. Let's see if we can think about what this looks like. Plus y squared equals 0. Now, if I complete the square here, got a 4 there, and I add a 4 over here. Notice what we've got here. We've got x minus 2 squared plus y squared equals 4. And this is a circle, we can see clearly, centered at 2, 0 with a radius of 2. Okay, so it's centered right here, and it has a radius of 2. So we can see what that looks like. Now, let's convert this to polar, though. So we've got this. We've got x squared plus y squared minus 4x equals 0. In place of the x squared, I'll write r squared. In place of x, I'll write r cosine theta. Now let me factor out the r. And I get that r equals 0 or r equals 4 cosine theta. Ah, okay. Now, we're shifting gears here to polar. So let's see what we've got now. We've got this double integral, and we've got f of, r cosine theta, r sine theta. Whoops, theta. Here we go. Sine theta, r dr d theta. Okay, now, so let's pick a radius. So I pick a radius, I pick an angle, theta, And I'm going from 0 to that circle. 0 to that circle. 0 to that circle. So look, for all these choices of theta, we're going from 0 to 4 cosine theta. Now notice, this circle is not centered at the origin, and our bounds are a little messier. Instead of going from 0 to whatever the radius is, now we're going from 0 to 4 cosine. Okay. Now, what does theta do? Well, there's different ways we could do this. I'm going to set theta to go from 0 to pi, because that's how we would complete this whole circle. We could go from negative pi over 2 to positive pi over 2, and we get the same thing. But another way to trace this circle out is to go from 0 to pi. But there we have the boundaries. What you have to do, and you can play around with this with your calculator to see how to get those bounds. You don't want to, you have to be careful not to overlook, you wouldn't want to go from 0 to 2 pi. Okay, so you want to just make sure you make one trace of the circle. And I'm going to do that with 0 to pi. Okay. Okay, so hopefully that gives you some idea about how to set these boundaries up.